Last time we established that there is a property, the context-free pumping property, that holds for all languages that are context-free. Recall that the context-free pumping property says that um, it says that. Let me just make sure I don't write it wrong. Okay, it says that there exists some number p inside of n, which we know is equal to 2 to the number of variables plus 1 inside of the context-free grammar, where for all s that come from A, if s is greater than or equal to p, then there exists u, v, x, y, and z inside of sigma star such that um, s equals u, v, x, y, z, and the length of vy is greater than 0, and the length of vxy is less than p, then for all I inside of n, u, v to the I, x, y to the I, z is inside of A. Okay? Now, what we want to do is we want to prove the negation of this property for some language A. This is a language that is not context-free. So that means that for all p in n, there exists a string s inside of A where the length of s is greater than p, where for all u, v, x, y, z inside of sigma star, where s equals u, v, x, y, z, and vy is greater than 0 and vxy is less than p, there exists an I inside of n where u, vi, x, yi, z is not inside of A. And what this will do, if we prove not CFPP on some language X, then that will imply that all is not equal to CFL, and thus that there is actually, if we look at our little picture, there's something right there. There's something outside of CFL. Now, what language are we going to choose? Well, what we're going to choose is the language 0 to the n, 1 to the n, and now here's the kicker, another 0 to the n. Now think for a moment why this is hard. So think about it from the perspective of a PDA. How might a PDA that worked on this attempt to work? Well, what it would do is it would push on the zeros, and then it would pop them off as it saw the ones. But if it did that, then it would forget how many there are by the time it looked at the second set of zeros. So maybe you might say, well, what I'll do is I'll push on the zeros, then pop them off, but like pop one off and like push on another one. The problem with that is that we can't go to the bottom of the stack and push something so that it's available after we look at all the ones. We can only push things to the top of the stack. So it's really the stack discipline that prevents us from being able to do this. So this is the language. So that's A. So now what we need to do is we are going to be given a P that we don't get to decide, because that's part of the for all. When there's a for all, that means that your enemy chooses it. When there's an exist, that means you pick it. So obviously what we need to do is we need to choose S. So let's choose 0 to the P, 1 to the P, 0 to the P. All right, so now what's going to happen is that we will be given u, v, x, y, and z. All right. So now what we need to know is and of course we know that the length of vy is greater than 0 and the length of vxy is less than p. So let's think about the fact that the length of vxy is less than p. What that means is that if we write out our string 0 to the p, 1 to the p, 0 to the p, then we need to divide this up into all the different ways that we could divide up the string. So let's divide it up based on how many different symbols are in Vxy. So option 1 is that Vxy contains 0 symbols. The only way that's possible is if it is equal to epsilon, but it can't be equal to epsilon because the length of Vy is greater than 0. So it can't contain 0 symbols. Okay, what if it contains, and when I say symbols, I mean, let's think about these ones. By the way, there's an equivalent version of this, which is a to the n, b to the n, c to the n. Let's actually prove it on this. So a to the n, b to the n, c to the n. And this is a to the n, b to the n, and c to the n. Okay. So what if it contains 4 things? And that's impossible because there aren't 4 things. Okay, because there's only 3. All right, what if Vxy contains 3 things? Well, if it contains 3 things, then that means Vxy has to be at a minimum a, b to the p, c. But the length of that is equal to p plus 2. But the length has to be less than p, so that's impossible. So it can't contain 3 things. All right, we're on a roll. All right, what if it contains 1 thing? Well, if it contains 1 thing, then what does that mean? That means it contains either only A's, only B's, or only P's. So it doesn't matter which one it chooses. Let's just assume that it contains A's. So we'll assume it has A's. If it has A's, then that means it has some number of A's. And if it has some number of A's, then let's just set I equal to 0. And if I equals 0, then that means it's going to have A, P minus K, however many were in it, and then BP, CP, and that is not part of the language because it's missing some A's. Now obviously if it only contains B's, we'd subtract some of those. If it only contains C's, we'd subtract some of those. All right, so we've broken up. And this contains 4. Actually, we really meant that contains more than 3 because it can't contain more than 3 because there's only 3. So that means that we only have to consider one last option, which is what if Vxy contains 2 things, 2 symbols. Well, if it contains 2 symbols, then here are the possibilities. It can contain A and C, which means that Vxy has to be at a minimum A, B, P, C, which actually means it contains 3 things, so that's impossible. Okay, because it can't contain 2 without containing 3. What if it contains A and B or B and C? So these 2 cases are going to work symmetrically. So let's just assume that it contains A, B, and we'll go from there. So that means that Vxy equals A to the K, B to the J. There's some number of A's and there's some number of B's. All right. Now, however many that is, let's not even worry about how to divide it up. What's going to happen is that we are going to set I equal to 0. If we set I equal to 0, then that means that we are going to get A to the F, B to the G, and C to the P, where F plus G is going to be less than 2P. We know that it's going to be less than 2P because we set I equal to 0, and Vxy contained some A's and some B's. We don't know which ones it contained. We haven't really thought about that. It doesn't really matter. Because if we set I equals to 0, that means that we drop away V and we drop away Y. Now, V and Y had to be greater than 0, so that means it had to contain something. And since it had to contain something, actually, you know what? Rather than writing it that way, let's write it a slightly different way. Let's not say that F plus G is less than 2P. let's write f has to be less than p, or g has to be less than p. And they might both be less than p. And so therefore, at I equals 0, the string is not in the language. So we have now gone meticulously through all the different things that u, v, x, y, and z could be made up of. And we've shown that it is impossible to follow the rules of the context-free pumping property and end up with something that is inside of the language. In other words, what we have done is we've shown that our picture looks like this. So we have all, which is the power set of sigma star. We have fin, and fin contains languages like 0, 1. Then we have reg, which contains languages like 0 star, 1 star. Then we have CFL, that contains things like 0 to the n, 1 to the n. Then outside of that, we have things like 0 to the n, 1 to the n, 0 to the n, or a to the n, b to the n, c to the n. Now notice that 0 to the n, 1 to the n, 0 to the n is very similar to another language that we like, which is 0 to the a, 1, 0 to the b, 1, 0 to the a plus b. So this language right here is the one that demonstrates that we can do unary addition. We can recognize true equations of the form a plus b equals a plus b. And this is not context-free either. And the reason why it's not context-free is that we can choose the string 0 to the p, 1, 0 to the p, 1, 0 to the 2p. And the problem is that we cannot make it so that the gap between we cannot make it so that we like straddle both sides of the gap and increase things, because we might be able to increase on one side, but we're not able to increase on the other side. All right. So we now know that there are and once we know that 0 to the n, 1 to the n, 0 to the n is not inside of CFL, we can then just union that with any other regular language, for instance, other than sigma star, and get an arbitrary number of other things that are also not inside of all. So that means that this set of things out here is infinitely large. So what we now know is that it is not possible for us to solve this kind of problem with a context-free language or with a context-free grammar, that there's a limit to these. So obviously what we need to do next is we need to start cutting up this space again, and we're going to cut it up into 2 more regions. And we'll do that next time.